In this video I want to show you the basic idea of QR decomposition. In later videos we will talk about how to decompose. In this video we only want to show the basic idea. Given a system of linear equations, that means A is a given coefficient matrix, a quadratic coefficient matrix, and B is a given right-hand side, and X is what we want to find, the solution of this linear system. And now we want to decompose A. That means we want to write A to be a product of a matrix Q and a matrix R. And Q is an orthogonal matrix and R is an upper triangular matrix. The LU decomposition, there we had, this was a lower triangular matrix and this was a upper triangular matrix. I don't know why in English literature QR decomposition and LU decomposition. In Germany we say LR decomposition and QR decomposition. For me that makes more sense. Okay, Q and R, and these matrices are to be found. But if we have found Q and R, then what do? Instead of writing A, we can write Q times R. And now we can multiply the equation with the inverse of Q. What is the inverse of Q? Because it's orthogonal. What is orthogonal? Orthogonal means the inverse is the same as the transpose, and transposing is very easy compared to inverting. Inverting is a very hard task we want to avoid, and so in this case we can write, and then here we have identity, and so we get on the right hand side it's also only a multiplication, and now we have an upper triangular matrix and we have a given right hand side, a little modified, but it's a right hand side, and then we can find this vector by back substitution. Okay, this is the basic idea. Now I want to recap a little what is orthogonal. What does that mean? That means that transpose times the matrix is identity, and always in the reverse order. Because if it's an inverse, then it's also true in this order. We only need this order. And where does the name of orthogonal comes from? You can interpret this equation also by the following. All the columns of Q are of length 1. So if you get the identity matrix, if you examine that product here for that entry, it's tested. The Euclidean length is 1. And these zeros are testing is the second column orthogonal to the first column, and this zero tests if the third column is orthogonal to the first column. So what do we want to see? We want to see an orthogonal matrix. This is an orthogonal matrix of size 2 by 2. Why is it orthogonal? We can test. The transpose of Q is keep the diagonal and exchange these entries. And now Q. And here we have 9 over 25 plus 16 over 25, what is 1. Here we have 12 over 25 minus 12 over 25, so it's 0. 12 divided by 25 minus 12 divided by 25. And 16 divided by 25 plus 9 divided by 25, which is 25 divided by 25, which is 1. And let's use alternatively that test. It's no more necessary. We did everything we had to do to show that it's orthogonal, but instead of doing the job in that way, we can also do it in the following way. What is the length of that vector? It's this entry squared plus that entry squared, and then the square root of that. 9 divided by 25 plus 16 divided by 25, which is 25 divided by 25, which is 1. And here the same, 16 plus 9, we get 25 divided by 25. And now they are orthogonal or they are not. Let's test. The dot product means multiply these entries, and add that. 12 divided by 25 minus 12 divided by 25, which is 0. Okay, now I showed you this example and maybe you notice a very specific structure. You see these entries are equal and these entries are also equal, but not completely equal. The sign differs. And this is true for all 2 by 2 orthogonal matrices. Indeed, but this special structure will not kept for sizes 3 by 3. And I want to talk about that. Maybe you see these examples and then later you will only remember this specific structure and then you confuse two things. So for 2 by 2, it's always true. Only this constellation is possible. That has to do with they have to be of length 1 and they have to be orthogonal. And for 2 vectors being orthogonal, there's only one way doing that, swapping the elements and spend 1 minus either at the first element or at the second element. So this is true indeed for 2 by 2 matrices, but not for 3 by 3 matrices. Let's write down an example of a 3 by 3 orthogonal matrix. This is a 3 by 3 matrix and this one is also orthogonal. The digits are rounded versions, so if you recalculate it will not be exactly true, but that has to do with rounding errors. Square this entry, square this entry, square this entry, and then sum them and the result will be 1. Here we have 0.64, here we have more or less 0.25, and here we have more or less 0.1, and if you add these 3 entries, then you will get a 1. Also here, this is 0.8 more or less, this is 0.05 more or less, and this is 0.2 more or less, and if you add these 3 numbers, you get 1. And if you do the dot product, that times that, plus that times that, plus that times that, you will get a 0. And also here, 0, and also here, 0. So this is an orthogonal matrix, but there is not such a specific structures as we have seen for 2 by 2 matrices. Okay. The open question is, how can we find Q and R? A is given and we want to find Q and R, and if we have Q and R, then we can take the benefit out of it. But how can we find? This question we will not answer in that video, but in the videos following. There will be the householder transformation, which will give us a QR decomposition, and alternatively there will be the givens transformations, and they will also give us a Q and a R, so we can choose which one do we want to choose, and depending on the situation, sometimes this one is the better one and sometimes this one is the better one. Okay, so now I want to show you on the computer one example for hopefully better understanding the basic idea of the QR decomposition. Let's start with that matrix. And now we can get the QR decomposition of A. There's a MATLAB command, which is QR, okay? And we will later understand what's going on if one calls that, okay? We only want to check the result. We have a matrix Q, this one, and we have a matrix R. R is upper triangular and Q is an orthogonal matrix. Why is it orthogonal? Because if we check the length, this entry squared is more or less 0.64. This entry squared is more or less 0.1. So sum these, so we have 0.74, and this one squared is more or less 0.3. And sum these entries, it will be 1. And also here, square, 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 and add. It will be 1, square, 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 and add. So this is 1. We can do that also with a MATLAB command. Square the entries of the first line, square the entries of the second line, and square the entries of the third line, and add these three numbers, and it will be exactly 1. So let's check if Q times R is indeed A. Yes, it is. 2, 5, 10, 2, 5, 10, 5, 8, 6, 5, 8, 6, and the first line is 7, 5, 5, 7, 5, 5. Now let's have a right-hand side. And now we want the solution of the system A times what is B. The answer is this. But how can we get this answer? We can multiply the right-hand side by Q transposed, and then we can call back substitution for Q transposed times B. Yes, I'm in the wrong directory. Now I change the directory, now I can call, and here we get, by calling back substitution, the desired solution. Okay, this is the basic idea of the QR decomposition, and in the later videos we will talk how to find the QR decomposition.